Hi, welcome to my channel. Today I'm going to discuss about capacitors. Okay, capacitor is an electronic component that is used to store charges and hence it consists of electrical energy. So capacitor actually, consists of two parallel plates and the gap between the parallel plates is filled by using a dielectric material. I'll discuss about the dielectric materials later and the effect of dielectric material separately I'll discuss. First, we'll think about how to charge a capacitor, how can it be discharged and used as an DC power supply. Okay, now capacitor consists of parallel plates. The gap between the capacitor is filled with dielectric material. Now, first you should charge the capacitor. If you are going to use the capacitor as a DC power supply, capacitor can be used in many different ways as blocking capacitors in amplifiers, bypass capacitors that allows only, looks like, actually it won't allow, but it looks like allow AC signal and blocks the DC signal, and it can be used as a smoothing circuit in rectifiers. So there are a lot of applications, but here I mainly discuss about, these lessons mainly focused on Edexcel, Cambridge International Baccalaureate syllabuses and AQA also. They are mostly the questions based on using a capacitor as a DC power supply. When you charge a capacitor, it consists of electrical energy. So later, a charged capacitor can be used as a DC power supply. Okay, so when you are charging a capacitor, what should we do? It should be connected to a DC power supply. So when a capacitor is connected to a DC power supply, what happens? The DC power supply will apply a voltage across the plates of the capacitor and there will be electric field. So electrons of these plates, first if I say this as plate X and this is as a plate Y. So electrons will be transferred from plate X to the DC power supply. So when the plate X loses some electrons, that plate will become positively charged. So the positive charge will stay inside inner plate of the inner surface of the plate X. So these positive charges will induce negative charges inside, and positive charges of the plate Y will stay on the outer surface of the plate Y. So this will consist of positive charges on the outer surface. Now, negative terminal of the DC power supply consists of electrons. So the electrons will flow from here to the outer surface of the plate Y and neutralize it. So effectively, the plate Y gained electrons and the plate X loses electrons. So the plate which lost electrons will become positively charged and the plate Y which gains electron will become negatively charged. This is called charging a capacitor. So when you are store charge or when you are charging a capacitor, actually what happens, electrons will be transferred from one plate of the capacitor to the other plate through the external circuit. So that is called charging a capacitor. It asked in the exam papers, they asked what is meant by charging a capacitor. So actually charging a capacitor means transferring electrons from one plate of the capacitor to the other plate through the external circuit. So in the region between the capacitor plates is filled with a dielectric material. Dielectric material is actually an insulator. Actually, it's an insulator. So electrons can't flow inside. Only thing they can flow through the external circuit. So the electrons are flowing from plate X to Y during the charging process. So the electrons are flowing this way. So when electrons are flowing this way, according to the conventional sign of current, there will be current flow in opposite direction. So there will be current flow in opposite direction. So it looks like current is flowing from positive terminal of the DC power supply to plate X and also from the plate Y to the negative terminal of the DC power supply. Okay, so what will happen to this current? Will it remain constant during the charging process? We are going to analyze it next. Okay, so I can draw a circuit during the charging process. So this is the capacitor. And this is the total resistance of the circuit. So what do you mean by total resistance of the circuit? Means that resistance includes all the resistive parts of the circuit. So that resistance R is actually it includes the internal resistance of the cell, total resistance of the connecting wires, resistance of the terminals where the wires are connected to the capacitor, everything together, I put it as capital R. Because during the charging process, the same current will flow through all the resistive parts of the circuit. So they are in series, all the resistive parts are in series. So I can imagine, even though it consists of internal resistance, I can include that resistance also. I can add that resistance with the total resistance of the circuit, and I can show it here as R. Okay, I can add additional resistor also, because to slow down the charging process due to certain reason. When we are doing practical, we add some resistors in the kilo ohm order, something like 20 kilo ohm or 30 kilo ohm, like that. Everything together is shown by capital R. Okay, so if I say the EMF of the DC power supply is V naught, initially the capacitor has no charge. So if the capacitor has no charge, the voltage across it will be equal to 0. Okay, the capacitance is defined as C equal Q over V, where Q is the amount of charge displaced from one terminal or one plate of the capacitor to the other plate. That is the amount of charge displaced. V is the voltage across the capacitor. So capacitance is defined by Q over V, where Q is the amount of charge displaced from one plate to the other plate. Okay, that is called charge of the capacitor. The amount of charge displaced from one plate to the other plate is called charge of the capacitor. I already told that in my previous videos. When there are separated charges, there will be potential difference across them. Say for example, if you have a charge here plus 5 coulomb, and here if you have a minus 2 coulomb, whatever it is, there will be potential difference between them. So you can go through my previous videos. There I am telling about the outcome of potential due to charges. So if one plate consists of positive charge and the other plate consists of same magnitude of negative charge, there will be potential difference across them, right? So during the charging process, initially there were no charge, so the voltage will be equal to 0. Because Q is 0, I can say Q equals CV. If Q is equal to 0, V is equal to 0. It has no charge initially. Okay, so no voltage. So voltage across the capacitor initially means when T equals 0, the voltage across the capacitor will be equal to 0. Okay, so what will be the initial voltage across the resistor when I switch on the circuit? So this is the switch. When I switch on the circuit, at that moment, voltage across the capacitor will be equal to 0. So the voltage across the resistor will be equal to V naught according to Kirchhoff's second law. I can see the voltage across the resistor VR, voltage across the capacitor VC. At any instant, I can say VR plus VC is equal to the EMF. I use it as V naught. Okay, so now what's happening? I told electrons will flow, so there will be current flow. So when current flows at an instant, if I say the current flow is I at a particular time, but at a particular instant, if I say the current flow is I, then I can say VR equal to IR. So instead of VR, I can say IR plus this is the voltage across the capacitor, VC equal to V naught. So make the I subject. I is equal to V naught minus Vc over R. Okay, so this equation clearly shows that the current flow won't be a constant. When the capacitor gains more and more charge according to Q equals CV, but I'm using VC for the voltage across the capacitor. So I can say according to Q equals CVC, VC is the voltage across the capacitor, Q is the charge of the capacitor, the amount of charge displaced. So when the charge of the capacitor increases, VC will increase. When the VC increases, V naught minus VC will decrease. So that means current will decrease. Okay, so when will it come to end, the charging process? When the voltage across the capacitor Vc becomes equal to V naught. That is, the voltage across the capacitor becomes equal to EMF of the DC power supply. Current flow will become equal to 0. So current flow becomes equal to 0 means the charging process will come to end. Okay, so what's the initial current during the charging process? When I close the switch, at that moment, initial current, what will it be? I can say initially there's no voltage across the capacitor because it has no charge initially. So the initial current we normally denote by I naught, that will be equal to V naught over R. Better remember this. Okay, this is the initial current of the charging circuit. Finally, what will be the voltage across the capacitor? That will be equal to EMF of the DC power supply. That happens when current becomes equal to 0. Okay, so I told that current will decrease during the charging process. How will it decrease? What will be the relationship between current and time during the discharging process? Okay, that is given by I equal I naught e to the power minus T over RC. So the current decreases during the charging process. I showed it just now. How will it decrease? The current will decrease exponentially. I can derive this equation by using differential equation, but that is not in the syllabus. I'll put it as a separate video, that mathematical part. But current will decrease exponentially, right? So exponentially it decreases means if I plot a graph of current against time, the graph will be like this. So this is I naught, that's the initial current when time t equals 0. Then it will decrease exponentially. The RC is called the time constant of the charging circuit, time constant of the charging circuit. Okay, why it is called time constant means it is constant, its unit is same as the unit of time. So that's the reason it's called time constant, because it's constant for a given charging circuit. R is constant, C is constant. So RC is constant. The unit of RC, that will be same as unit of time, that is second. We'll see that. Unit of RC is equal to, unit of R is ohm, unit of C, capacitance, is equal to farad. So if I think about R equal VOY, I can say ohm is equal to volt per ampere. And this is the unit of capacitance, farad. According to Q equal CV, farad is equal to coulomb per volt, coulomb per volt. Now look at here, volt per volt will get cancelled. You will get coulomb per ampere. If you think about Q equal IT, coulomb per ampere, Q over I, is it? That will be the unit of time, second. Okay, so the unit of RC is equal to second and it is constant. So that's the reason it is called time constant. Okay, so how the current varies? What's the outcome of time constant? How the time constant is going to decide the current flow? Okay, that also can be shown like this. Okay, now initially when t equals 0, the current flow will be I is equal to I naught e to the power 0. E to the power 0 over RC, we know 0 is equal to 1, e to the power 0 is 1. So initial current I will be equal to I naught. Okay, so I told this time constant RC has a unit of seconds. Say for example, we are using a resistance of 20,000. So RC 20,000, and imagine we are using a capacitor of 1000 microfarad. So 1000 microfarad 10 to the power minus 6, that will be equal to how much? That is here 7. So it's going to be 20 seconds. So RC has a value something related to time, 20 seconds. So imagine every 20 seconds what's going to happen. Every 20 seconds of the charging process, how the current is going to vary. That's what I'm going to analyze now. So you know the value of RC is 20 seconds, yeah, if you solve it. Right, so every 20-second interval, if I consider every 20-second time, if I consider how the current is going to change. Okay, so I can say when t equals 0, I showed I is equal to I naught. When t, the time becomes equal to, say I showed an example, 20 seconds. So generally I'll say when the time t becomes equal to RC, what will be the current flow? I will be equal to I naught e to the power minus RC over RC. So that is going to be I naught e to the power minus 1. That is going to be 1 over e of I naught. You know the value of E. E is, you can get it in the calculator. The value of E is something 2.70, is it? The value of E is 2.718. Okay. So after time of RC, the current will become 1 over E of I naught. Okay, so think about the previous my example, 20 seconds I got RC. So after 20 seconds, that will be 1 over E of the initial current. After 40 seconds from the starting time, that is after time t equal 2 RC, what will happen to the current flow when t becomes equal to 2 RC? I will be equal to I naught e to the power minus 2RC over RC. That is going to be I naught e to the power minus 2. That is going to be I naught over E squared. Yes, I naught over E squared. This I can write 1 over E of I naught over E. So I naught over E is, I can call this as in I1. If I say this is I1, if I say this is I2. So I2 is going to be, look at here, 1 over E of I1. See, initial current was I naught. Then after a time duration of 1 RC, the current flow becomes 1 over E of the initial current. That is I called I1. After another time interval of RC, the current drops to 1 over E of the previous current I1. Okay, same way I can show when time becomes 3 RC. Okay, I'll show it here. When time becomes 3 RC, t equal 3 RC, what will be the current flow? I3 is equal to I naught e to the power minus 3 RC over RC. That is going to be I naught e to the power minus 3. That is I naught over e to the power 3. This I can write I 1 over e of I naught over E squared. I naught over E squared is this one, is it? I2. So it's becoming 1 over E of I2 is I3. So that means every time interval that is equal to RC, the current is dropping to 1 over E of the previous current. Okay, then what is the amount of 1 over E? 1 over E of the value of 1 over E will be equal to you will see that 1 over E is equal to 0.367. That is almost 0.37. 1 over E is equal to 0.37. Okay, so I can say like this. During every time interval that is equal to RC, the current is dropping to 0.37 fraction of the previous current. Or if I want to tell it in percentage, I can say during every time interval that is equal to RC, current will decrease to 37% of the previous current. Okay, so that's the way we define. Based on this idea only, we define the time constant. How do we define the time constant of the charging circuit? How do we define the average time taken for the current, the charging current, to drop to 37% of the previous current? So that's the way time constant is defined. Okay, right. So next we are going to analyze how the voltage across the capacitor varies during the charging process. Okay, so we know that current decreases exponentially. So current decreases exponentially means how is it the current flow is affected by the time constant. Also, we know that. So when the time constant of a charging circuit is larger, that means it's going to take more time to charge the capacitor. If the time constant is shorter or smaller, it will take lower time to charge the capacitor. But anyway, the final charge or the final voltage across the capacitor will be equal to the EMF of the DC power supply. So the final charge of the capacitor also will be same as Q equal C times V naught. That's the final charge. Is it Q equal C times V naught? Because the final voltage does not depend on the time duration. That is actually going to take more time if the time constant is larger, but the final voltage will be same as the EMF of the DC power supply. So if I plot a graph of current against time, the area under the graph, area covered by the graph and the time axis will give the amount of charge flown in the circuit. The amount of charge flown in the circuit is the charge stored in the capacitor. The amount of charge flows will be the charge stored in the capacitor. So the initial current I gave it I naught is equal to V naught over R, right? So if you are using higher resistance, that is time constant for a given capacitor, if you are using higher resistance during the charging process, initial current will be smaller. If you are using larger resistance, initial current will be larger resistance means initial current will be smaller, and smaller resistance means initial current will be higher. So if I use a smaller resistance, initial current will be maybe I naught dash, and if you are using higher resistance, initial current may be smaller. Let it be I naught. But area under the graph will be the same for both. The reason area under the graph gives the amount of energy, amount of charge stored in the capacitor. So both should have the same area. So which has smaller initial current will take longer time to charge, and the area will become this way, the shape. And the lower resistance will have higher initial current, so the graph will become like this. But anyway, the area under the both graphs should be the same. Okay, both should have the same area under the graph, because area under the graph gives the charge flown in the circuit. That will be the charge stored in the capacitor. Okay. Now, how the voltage across the capacitor and the voltage across the total resistance of the circuit varies with time. Okay, so I'll consider a capacitor and the total resistance of the circuit, let it be R, and the EMF of the DC power supply, V naught. So initially the circuit was on, and this is resistance R. This is the capacitance. Okay, when you switch on the circuit, when you close the circuit, uh, the charging process will be started. So at an instant, the voltage across the resistor VR, voltage across the capacitor VC means I already told that VR plus VC should be equal to EMF according to Kirchhoff's second law. So I can say VR plus VC should be equal to EMF, that is V naught. Okay, that should be equal to V naught. But I know that I already showed it. The current flow in the circuit during charging process will decrease exponentially. So current will decrease I equal I naught e to the power minus t over RC according to this equation. Also, I know that the voltage across the resistor is given by V equal IR, VR equal IR. So, since the current flow decreases exponentially and R is a constant, voltage across the resistor will decrease exponentially. So, for the voltage across the resistor, I can write an equation at an instant. This is for resistor I am writing. V equal V naught e to the power minus T over RC. I can write for resistor or total resistance. Resistor, or for the total resistance, I can say the voltage across it will vary exponentially. So the voltage across the capacitor I can find like V naught e to the power minus T over RC plus VC equal to V naught. So VC will be equal to, take it to the other side, V naught into 1 minus e to the power minus T over RC. So by using this, I can find the voltage across the capacitor at any time t. If I plot a graph for the voltage across the resistor, so I generally say voltage, this is time. For the resistor, it's going to be exponentially decaying graph. This is for the resistor. And this is the initial volt, that's the voltage across the EMF of the DC power supply. So for the capacitor, the graph will be like this because this should be a constant. The VR plus VC is always constant. So the voltage across the capacitor will be initially 0 and it will vary like this. Okay, this is for capacitor. Okay, I told that a charged capacitor consists of charge and electrical energy. Okay, what's the origin of this electrical energy stored in the capacitor? You know, during the charging process, battery is doing work, or the DC power supply, which is used to which is used to charge the capacitor, is doing work. Okay, what's the reason for the work done? See, now these are initially the plates of the capacitor. They are initially neutral plates. They have same number of positive charges and negative charges, so they are neutral. Now, when you are charging process, I told the DC power supply is removing some electrons from the plate X. So when the electrons are removed, it's something like ionizing. Is it something like, not ionizing, but it's something like that. You are removing the electron means the existing positive charges or nucleus of the plate X will try to attract them back. So that means the battery should do work to overcome that electrostatic repulsive force. Same way, the DC power supply is transferring electrons to the plate Y. That means the existing charges of the electrons of the plate Y, the atoms of the plate Y consist of electrons in their orbit. So those electrons will repel the electrons those are flowing from here. So again, battery should do work to overcome that electrostatic repulsive force. That means in overall, the DC power supply or battery is doing work to remove the electron and to add the electron to the plate X. There's the work done. Okay, so that work done, not 100% everything, a part of that work done will be stored in the capacitor in the form of electrical energy. Okay, we'll try to get a expression or the expression or the formula for the energy stored in a capacitor. Say if at an instant during the charging process, at a particular instant, the voltage across the capacitor is V, the EMF of the DC power supply is V naught. So due to the charge already stored in it, there is voltage V, right? The voltage across the plates is V due to the charges already stored in it, but still the charging process is continuing, right? So imagine a charge of dq, a charge of delta q is transferred. Now it's removed from here. So the amount of work the battery should do to transfer that work is given by a small work done delta W, you know W equal QV. The required work done delta W is equal to delta Q times V, right? That's the voltage across the plates, right? Now imagine at that instant the amount of charge of the capacitor or the charge stored in the plate X is Q. So we know that according to Q equals CV, I can say Q equals C times C is the capacitance into V. So instead of V, I can say Q over C. So that is going to be delta Q times, instead of V, I can say Q over C. That is 1 over C Q dQ is the amount of work done at that instant when the DC power supply is transferring a charge delta Q from plate X to plate Y. Okay, so it's continuing the charging process. The total work done is the summation. It's a scalar quantity work done. So the summation will become integral. So that is the total work done, right, will be stored in the capacitor in the form of energy. So the energy stored in the capacitor is going to be integral of 1 over C Q dQ. Initially, the charge of the capacitor was 0. Finally, the charge becomes Q. So that will be 1 over C Q squared over 2, and the limits are 0 to Q. So it will become Q squared over 2C. But we know that Q equal CV. So substitute that. Instead of Q squared, I can say C squared, V squared over 2C. So that's going to be E is equal to half Q equals CV, Q squared, C squared, V squared over C, half CV squared. That also energy stored in the capacitor. Or I can say C equal Q over V. If I substitute that here, E equal Q squared over 2 times. Instead of C, I can substitute Q over V. So that Q squared get cancelled. V will go up. It will become half QV. Okay. So that is going to be the general equation for energy stored in a capacitor. Okay, so we know that a charged capacitor consists of energy. So there are 3 equations for energy. Energy equal half QV or half CV squared or Q squared over 2C. We can use one of it depending on the questions and the data given. Right. Now, so a charged capacitor, when you connect it to a component, something like resistor or LED or bulb, the capacitor will lose its charge. Why that happens? Now, for example, a charged capacitor consists of positive terminals on one of its plate and negative positive charges in one of the plates and the negative charges on the other plate, right? So if you connect this one to a component, anything bulb or LED, or just I draw a resistance R. So this is like a battery. It's going to function like a battery. If you think about a normal DC power supply, a battery, they are also, due to chemical reaction, this positive terminal consists of positive ions and the negative terminal consists of free electrons. And when you connect it to a component through the external circuit, the electrons flow from negative terminal to positive terminal, yeah, and there will be current flow in other way, opposite direction. So when you compare this DC power supply, something like a battery, to the charged capacitor, that also same thing like this one. So that also can supply or translates electrons when the terminals are connected to a component. It can be a bulb or whatever it is, because it consists of electrical energy also. It consists of chemical energy, and due to the chemical reaction, it can supply electrical energy. But here it consists of electrical energy due to work done by the DC power supply during the charging process, right? So when we connect a component, electrons will flow from the negative plate to the positive plate. So there will be current flow in opposite direction to the flow of electrons. So current will flow in this direction. There will be current flow in this direction. Okay, so this current flow, will it remain constant or how does it change with time? The current flow decreases exponentially. Actually, when you think about a DC power supply, how does it how the current flow changes with time. If you are given a battery, say a dry cell, and if you connect a particular resistance, right? If you connect a particular resistance, a component which has resistance R, and if you use a data logger to measure the current during a longer time period, and there you can't predict the current flow, how it is going to decrease when the chemical or when the charges of the DC power supply is used up. Current will decrease. We know when you are using a DC power supply like a battery for longer time, we know that the current flow decreases, but that has no proper equation because it's a chemical reaction. The charges are created due to chemical reaction. Current will decrease, but it can fluctuate and decrease. Okay, but here it has a proper mathematical model during the discharging process, that is during the current flow. When you connect the charge capacitor to a component, current will flow and the capacitor will lose its charge, that is called discharging a capacitor. So during that discharging process, current varies in a proper mathematical format, that also exponential decay, right? So during the discharging process, that is when a charge capacitor is used, the current will decrease according to I equal I naught e to the power minus T over C. But for a DC power supply, something like a battery, you can't get an equation like that. It will decrease, we know current will decrease, but not in any proper mathematical format. So here the current decreases this way, where RC is called time constant of the discharging circuit. Same meaning. There, earlier I told, that's a time constant of the charging circuit. This is the time constant of the discharging circuit. Same way I can show the definition of time constant of the discharging circuit. I can say the average time taken for the discharging current to drop to 37% of the initial current of the previous current. Okay, same format, mathematical model also same like charging current. So I equal I naught e to the power minus T over C. So the voltage across the component, that is I can say voltage across the component VR. So that is equal to VR equal IR. So voltage across the component also will decrease exponentially. That is, I can say I naught R is V naught e to the power minus T over RC. So the voltage across the component will decrease exponentially, means the voltage across the component is same as the voltage across the capacitor. So voltage across the capacitor also will decrease exponentially during the discharging process. Voltage across the capacitor, I got it for voltage across the resistor, but voltage across the resistor is same as the voltage across the capacitor. So voltage across the capacitor also will decrease exponentially during the discharging process. Discharging process means we are using the charge or energy stored in the capacitor, something like a DC power supply, or discharging means capacitor losing its charge. Okay, so how the charge of the capacitor will vary? So we know that Q equal CV. So voltage of the capacitor will decrease exponentially. So charge of the capacitor is given by Q equals C times, instead of V I can write V naught e to the power minus T over C. So that I can say Q naught e to the V, C into V naught is Q naught. So Q naught into T over C. That means charge stored in the capacitor also will decrease exponentially. Okay, so remember that during the discharging process, voltage across the capacitor will decrease exponentially. Charge stored in the capacitor will decrease exponentially. And also, current flow during the discharging process also will decrease exponentially. Okay. Okay, so as a summary, I can say during the charging process, at the moment when you start charging process, the initial current flow in the circuit So the initial current flow in the circuit is given by I naught equal the EMF over total resistance of the circuit. That is the initial current flow. Then this current flow will decrease exponentially. Okay, so it follows the equation I equal I naught e to the power minus T over RC. So the current flow will decrease exponentially like this according to this equation, where RC is called time constant. Its unit is also second. So voltage across the resistor, voltage across the resistor at any instant is given by V equal IR. So the voltage across the resistor also will decrease exponentially according to V naught e to the power minus T over RC. So voltage across the capacitor, what will happen during the charging process? What will happen to the voltage across the capacitor? Voltage across the capacitor will increase according to Vc equal V naught into 1 minus e to the power minus T over RC. According to that, the voltage across the capacitor will increase. Okay, so these are the equations related to charging process. Okay, so what's the origin of energy stored in a capacitor? So during the charging process, battery or the DC power supply is doing work to overcome the electrostatic force uh, from the existing atoms or the new electrons and nuclei of the plates. So due to the work done, there will be energy stored in the capacitor. So energy stored in the capacitor is given by E equal half QV, where Q is the charge of the capacitor, V is the voltage across the capacitor, or we can say half CV squared or Q squared over 2C. These are the energy stored in the capacitor. Right. Now, what do you mean by discharging a capacitor? Discharging a capacitor means whenever capacitor loses its charge. How that happens? When you connect the terminals of a capacitor, we can use a charged capacitor like a DC power supply, right? So when the terminals of a capacitor is connected to a component, something like this, connected to a component, maybe bulb or whatever it is, connected to a component which has resistance R. So the charge of the capacitor will flow from the negative terminal to positive terminal through the external circuit, or the current will flow from positive terminal to the negative terminal through the external circuit. So during that time, the charge of the capacitor will decrease. So charge of the capacitor will decrease exponentially according to Q equal Q naught e to the power minus T over RC. Same way, the voltage across the capacitor also will decrease according to V equal V naught e to the power minus T over RC. V naught is the initial voltage across the capacitor. The current flow also will decrease exponentially. I equal I naught e to the power minus T over RC. All three factors will decrease exponentially during the discharging process according to these exponential equations. Okay, so next there's one thing called half-life of the charging circuit or half-life of the discharging circuit. Okay, during the charging process, only one factor decreases exponentially, that is the current flow, charging current flow. Okay, what's the half-life of the charging circuit means? The average time taken for the current flow to drop to half of the previous value or 50% of the previous value. That is only for current, because during the charging process, only the current will decrease exponentially. Voltage across the capacitor will increase, but the voltage across the resistor will decrease exponentially. That okay. But we normally define the half-life of the charging circuit by using current flow. The average time taken for the charging current to drop to 50% or half of the previous current, and we can get an expression for that. Say for example, the initial current is given by I naught. At a time t, the current is given by I equal I naught e to the power minus T over C. So when t equals 0, When t equals 0, the current I is going to be I naught. So how long will it take for the current flow to drop to I naught by 2? That time is called the half-life. So I can say when t equal t half, half-life is notated by this way, half-life, t half, the current flow I will become equal to I naught by 2. Substitute these things in this equation. So I naught by 2 will be equal to I naught e to the power minus t half over RC. I naught will get cancelled. Half equal e to the power minus t half over RC. You know how to do this. This can be written 1 over. This can be written as half equal 1 over e to the power t half over RC. Cross multiply, right? Cross multiply. So e to the power t half over RC equal to 2. Okay, I can remove e. You know, remove is not a proper word, but I can say like from this equation, I can eliminate e by taking natural logarithm, operate by natural logarithm on both sides. So ln e will become, the e will vanish, you know that. So t half over rc will become equal to ln2. So t half will be equal to rc ln2. Okay, so this is the half-life of the charging circuit. So half-life of the charging circuit depends on the time constant. RC is the time constant and a number. ln2 is a number. Okay. Same way I can get, same way, nothing different. Same method I can get half-life of the discharging circuit. So for that I can use any one of it. Current or voltage across the capacitor or charge of the capacitor. All three factors decreases exponentially. So I can take one of it and derive the same expression for the half-life of the discharging circuit. Okay. Okay, we will discuss some practice questions, calculations in my next video.